Here's one, polar coordinates, right? This is a good example because it illustrates something you guys want to ask about once you think of it. So the thing you want to ask about is, suppose the derivative is non-zero. Suppose that the Jacobian matrix is invertible on a whole set. Suppose that the determinant's non-zero everywhere on a set. Does that then imply that there's a global inverse for the function? Wouldn't it be nice if it did? But here's why it doesn't. So here you can calculate the polar coordinate. Here's the polar coordinate map, right? You calculate. Come on, where's my? Oh, here it is. Here's my Jacobian matrix, right? Take the determinant of this. What's it give you? R cosine squared plus R sine squared. So the determinant is R. So polar coordinates are invertible. Where? Locally. Everywhere except one place. The center, right? The origin. But you know what happens if you try to find an inverse for polar coordinates? You get something like this, right? Which makes sense, except for one thing. There's a place where the angle has to jump 2 pi. And if the angle has to jump 2 pi someplace, that means it's not continuous there, right? But you guys proved that differentiable implies continuous, even for maps. So if there's a place where the angle function jumps, where it's discontinuous, it's certainly not differentiable there, right? So there cannot be a global inverse for the thing. Not a global inverse which is continuous anyway, much less differentiable. That angle defect is real. We have to deal with it. So calculus can solve local problems, but it can't solve global problems. Global problems are always with us, and they're set theory. They don't stop being set theory because of calculus. I mean, they're... Here's another one. We have R3 to R3, AX, BY, CZ. So the derivative, so the Jacobian matrix is actually just ABC down the diagonal. And we get the determinants ABC, which is non-zero for all x, y, z in R3, which means that this function is locally invertible everywhere, right? And in fact, this one is really invertible everywhere, right? The Jacobian matrix is everywhere invertible, and in fact, we can find a global inverse. Because if you solve this equal to that for x, y, z, you just get u over a, v over b, w over c. I'm not saying anything terribly surprising here. If you want to undo multiplication by a, you divide by a. Right? And as long as neither a, b, or c is 0, we're okay. All right, I'm sorry. I'm sorry I even went over this example in class. It's so silly. Example 8 returns to the question of linear algebra, right? So I'm going to go on. So the implicit function theorem. What's the implicit function theorem? These are related problems, and so as with the inverse function theorem, I think it's helpful to go back to the place we first face it in calculus 1 or calculus 3, perhaps. Suppose, probably calculus 1. You've got x squared plus y squared equal to 1, right? You want to solve for y. What happens? We get two answers, right? So, right, we get the positive square root and we get the negative square root, right? What happened those 2 points, right? Like what's the deal? Why can't we find y as a function of x locally there?
We don't know how local.
What's that?
We don't know how local.
How local?
It's on one side or the other.
Well, if I could, so if I could, if I could find y equals to f of x, that was here, right? Like on some little interval there. Then it would have to match the circle, right? But if it has to match the circle, it necessarily fails the vertical line test See, I automatically have to output 2 inputs for 1 output if I include those places where there's a vertical tangent. So this is the trouble. Somehow vertical tangents don't allow us to write y as a function of x for graphs of equations in the plane. Right? So the question then is, what does that have to do with calculus? Right? I mean, you can understand the picture and the solving for, and you can look, and you can understand it like, oh, it's where the, you know, the place where there's an issue is where the plus and minus solutions meet, right? Algebraically, we can expect the place we can't find a local function is the place in between, sort of, it's the time in between times, right? It's that place where the different cases in our solution tend to meet. That's probably where we're going to find a point where we can't find y as a function of x. But what does that have to do with calculus is the question, right? Let me show you. So again, just to drive the point home, if you want to solve for y near 1, 0, it's impossible to find a single function which reproduces it on some open disk centered at 1, 0. So what's going on here? So, you know, assume that y is equal to a function of x. We can do what's called implicit differentiation in calculus 1, right? We implicitly differentiate that. We give what? 2x plus 2y dy dx equal to 0, which says dy dx must be what? Minus x over y. Oh, man. Well, that's very troubling. If y is equal to 0, this expression is sure hard to live by, right? I mean, that we're kind of in trouble there. So, apparently, the singularity in the derivative indicates we might have trouble solving an equation one variable for a function of the remaining variables. Now, I don't think this is yet really explained to you. I mean, this equation right here is very telling. This is what kind of generalizes. See, the reason we couldn't solve for y as a function of x is what? The coefficient, whatever appeared here, was 0. Where this coefficient is 0 is where we get into trouble. Right? That's the defect. When y is 0, I can't solve for dy dx. That's what we want to generalize, that idea. So here it is. So suppose we have not one equation, but n equations, all right? And suppose we're looking at them, they have function, you know, n equations with functions x1 through xm and y1 through yn, all right? And what I want to do is I want to see, can I solve this system of equations, right? Can I eliminate y and can I write the y's as functions of the x's, right? So what I'm trying to find is a mapping H which goes from Rn to Rn, where g of xy is equal to k. K is the vector of constants here, okay? Such that when I plug y equals h of x, all right, into the equation, what happens? I get, oh, curses, I can't see it all of a sudden. Oh, man, I'm sorry, guys. Where's I'm missing something. Oh, here it is. I'm sorry. I was looking, see, what was messing with me, guys, is I was looking for g of x comma h of x, and I've just written it in a slightly different way. So the point is, if we plug h of x into here, we have g of x comma h of x equals to k, which is to say that I have written y as a function of x so that it solves the system of equations. Again, not to beat a dead horse, but we're trying to solve this system of equations for the y's in terms of the x's. Just like I tried to solve x squared plus y squared equals to 1 for y. Okay? There I had one equation. Now I've had n of them. All right. So in this kind of problem, it's helpful to use some kind of sneaky notation. So here's what it looked. So just to revisit my motivating example, we had g was just x squared plus y squared, right? So like partial g partial x dx dx plus partial g partial y dy dy was equal to 0. If I had y as a function of x, and I look at g of y of x, then by the chain rule I get this. Okay, and so of course dx dx was 1, partial g partial x was 2x, partial g partial y was 2y. You can see the condition that we need was that partial g partial y was non-zero. Right. You might guess what condition we're going to need to solve for the y variables then. So this notation, I guess I need to, come on, where's the, stink. Ah! What? Ooh, okay. So sorry. I haven't actually, oh, I'm an idiot. Let's go on. The notation I want is on the next page. I don't need it yet. When my brain is jumping, I'm thinking I want to define x and y abstractly. X and y are not abstract yet. These are just single variables. They become vectors of variables on the next page is the thing that's messing with my head. So we want to solve g of xy equals to k. How do you do it? Replace it with its linearization. Don't solve the equation, solve the linearization of the equation. So g of xy can be replaced with k plus the Jacobian matrix times that, right? This is the linearization of g at the point of interest. And then, how can I solve this? I want to solve for y as a function of x. So solve this equation for y. You can do it. Sometimes. That's when I need this notation. So partial g partial x will be this matrix. Partial g partial y will be that matrix. Totally natural. It's just the first m columns of g prime of a b. This is the last n columns of g prime a b. So g prime of a b is these two things concatenated, glued together. And so when I look at g prime of a b times the difference vector x minus a, x minus b, we got two pieces. You've got this piece and that piece. When you multiply this times x minus a comma y minus b, matrix multiplication gives you these terms. And then the question is, what do you need to solve for y? This is a matrix. This is an n by n matrix, a square matrix. How can we solve for y? We need that this is an invertible matrix, right? So if partial g partial y is at AB is invertible, then we can solve for y, and that should give us an approximation to the implicit function we're looking for. Just like that. Right? And so that's it. That's the implicit function theorem, is you can solve for y as a function of x if the defining equations take partial g partial y as an invertible matrix at that point, and that the function is continuously differentiable near the point in question. Here's the formal statement. Oh, what? Yowzers. Here it is. So it's just what I said. And again, you can actually converge to the implicit function by iterating, just like we did before. By again approximating and approximating and approximating and just doing it over and over and over again. Now this proof down here, I should share with you while I got this out before my voice completely goes. An interesting fact, this proof has nothing to do, little, if anything, to do with the argument I just gave. What this proof does is it shows you that if you know the inverse function theorem, you can prove the implicit function theorem. So inverse function theorem implies implicit function theorem. And the way you do that, excuse me, is you construct f as x comma g of xy like this. And if you do that, the Jacobian matrix of this, see now, notice that this is n dimensional. That's got n dimensions, that's got m dimensions. So we're going from m plus n to m plus n. This f is a function on Rm plus n. And its Jacobian matrix looks like this. The determinant of a block diagonal matrix is the product of the determinants of the diagonal. Consequently, this is invertible only if that's invertible, because the determinant is the determinant of that. And so by the inverse function theorem says this is invertible, f is invertible, only if the determinant of this thing is non-zero and is continuously differentiable. But the determinant of this being non-zero is the determinant of that being non-zero, which is exactly the condition needed for the implicit function theorem, that this vector partial derivatives be invertible. Invertible. And so that then you just work back and you get from the existence of the inverse function, it implies the existence of the implicit solution. All right, anyway. Let me try to redeem the day by doing at least one calculation for you guys. I warned you I would not prove these theorems, but I usually try to at least explain them worth something. So I'm sorry about today. Not my best day. So suppose you have x squared plus y squared plus z cubed plus w cubed equals to 7, and x, y, z plus w equal to 2. All right. Then you can ask questions like, can I solve for x and y as functions of z and w? That's a weird question. Or I could say, can I solve for z and w, right? So this I would usually write x equals to x of zw and y equals to y of zw, like that. Let's see here. So what is my g? Oh, I'm sorry. Thank you. No, I do want to be consistent, so I appreciate that. So what's g prime? So the way it works, we do partial g, partial x, right? Partial g, partial y, partial g, partial z, partial g, partial w. Okay? So what's that work out to here? Yeah, we got 2x and yz, and what do we got? xz, thank you. And then what?
3z squared, xy, 3w squared, and 1.
1. All right. So if we wanted to solve for x and y as a function of z and w, the question of whether or not we can do that, the implicit function theorem says we have to focus in on this piece right here. The question is that invertible? If that's invertible, that means I can solve for x and y as functions of z and w. So notation for that, usually something like, well, forget about notation. Partial, I'll say here's the notation, partial g x y. That was the notation. This is the notation I was just using. Sort of the notation I was just using in the notes. It's an okay notation. That would be 2x, 2y. I mean, if you don't like this notation, invent your own. Just tell me what you mean. And when is that invertible? So we've got 2x squared z, y squared z. So it looks like we've got 2x squared minus y squared z. So we better stay away from x equals to plus or minus y. Those are troublesome, right? And z equal to 0, also problem spot. But other than that, if we pick a point, we should be able to find a way to solve for x and y as a function of v and w, at least locally. Now, that doesn't mean you can actually do it, right? In the same way, if the function's continuous, you can anti-differentiate it. But that doesn't mean you can actually find an antiderivative, does it? It does not. That's a harder thing, to actually find the formula. Now, here's another question. So, what if you wanted to solve for, let's suppose we wanted to find y as a function of x and w, and z as a function of x and w. What will we need then? We'd have to look at partial g, partial y, z, right? So again, this non-zero implies can solve for x as a function of zw and y as a function of zw, at least locally. This one would be what? This one would be 2y xz, right? And what was the oh, 3, it's the middle. It's the middle too, isn't it? You notice I'm not really adhering to the strict ordering of the actual theorem that was given. I'm applying the idea of the theorem. I'm not insisting that the variables we're solving for be last in the list, right? Like we did x comma y, we solve for y. I'm suggesting that you can solve for any subset of the variables as long as it's as many variables as you have equations. Assuming that, again, the sub-Jacobian matrix, relevant sub-Jacobian matrix is invertible. Whatever that would require, you know. Now, there's yet another question you should ask in this kind of context, which is, okay, so, you know, what's partial y, partial x? I'm sorry, what's partial y, partial z here? Right? See, because there's two different notions of partial y, partial z. Down here, we could talk about partial y, partial z holding w fixed, right? Up here, we could talk about partial y, partial z holding, oh, curses. What's that? Yeah, w fixed. But I wanted to hold, yeah. Did I just do the same thing twice?
I think it's partial x, partial y.
Oh, I can't calculate partial y, partial z here. It doesn't make sense. Oh, when? Curses. I want to think about partial derivatives in x or w here, you know. So then I can ask, like, what's partial y, partial x holding w fixed? That would be a question I could ask. So the next sort of itch to scratch in here is if I do a partial differentiation in this world, right? How do I understand those? And how does that relate to the implicit function theorem? What I'm really trying to get to, and I'm not getting there fast enough or clear enough today, unfortunately, is that the implicit function theorem will justify some of these calculations you've seen in Calculus 3 with me that we did in terms of differentials. The long story short of it is basically you take the system of equations that you're given, you just calculate the total differential of the equations, and then you solve for the differentials you're interested in. And you can do that if and only if that relevant sub-matrix of the Jacobian is actually invertible. I'll try to show you guys that next time, though, so we're out of time. So, sorry, I seem to have somehow gotten behind. I think it's my own stupid fault. So sorry, guys. Oh, so I think the next homework can be due Friday, if that's all right with you guys. I think we've covered all that for a few days. If you need extra time on it, just let me know. Mission 2. Mission 3 should be due a little bit later. So. Thanks, guys.